All right, so let's dive right into uh, this fascinating paper at the intersection of two really critical areas of machine learning,
Okay.
continual learning and adversarial robustness. Now, our listeners are probably already familiar with these areas, but
Indeed.
just to set the stage, this paper we're looking at is called Maintaining Adversarial Robustness in Continuous Learning. And it highlights a really surprising finding that robustness to these adversarial attacks, it's not a static thing.
Yeah.
It can actually be forgotten, much like performance on a task as a neural network learns sequentially.
Yeah, it's a bit counterintuitive, isn't it? You think that once you achieve robustness, that's it.
Yeah.
But this research really shows that it's a lot more dynamic,
Right.
especially in these continual learning scenarios.
Absolutely. And this brings us to this new challenge of continual robust learning. So how can we design these models that not only maintain
Yeah.
high performance across a series of tasks, but also retain robustness to these adversarial attacks?
Yeah. And this paper argues that we can, and they introduce an algorithm called double gradient projection, or DGP, to do just that.
Okay.
But before we get into their solution, it's worth taking a quick look at some of the existing techniques that kind of lay the groundwork for this.
Okay.
The authors draw inspiration from two key methods, input gradients regularization, or IGR, for robustness,
Right.
and gradient projection memory, or GPM, for continual learning.
Okay, so let's unpack those a little bit. IGR, if I remember correctly, aims to improve robustness by essentially smoothing out the gradients of the classification loss with respect to the input.
Yeah.
So the idea is if the model isn't overly sensitive to these tiny little changes in the input, it's less likely to be fooled by an adversarial example.
Precisely. IGR is making that decision boundary less susceptible to those subtle perturbations that attackers use.
Okay, and then we have GPM, which tackles that continual learning problem of catastrophic forgetting. And it does this by constraining how the model's weights are updated as it learns new tasks.
That's right. GPM essentially identifies those important directions in the gradient space that are really critical for preserving the performance on past tasks.
Okay.
And then it projects weight updates in a way that avoids messing with those important directions.
So essentially, the authors are taking inspiration from both IGR and GPM and combining those.
Exactly.
Their hypothesis seems to be that if you can stabilize these smoothed gradients from IGR during continual learning, then you can maintain those robustness gains.
Yeah, and that's where DGP comes in.
Oh.
It's designed to do just that, stabilize both the final outputs and the smooth gradients during continual learning.
And this is where it gets really interesting. DGP uses a technique called singular value decomposition,
Right.
or SVD, to find and store what they call important directions in the gradient space. And these are represented as basis vectors.
You can think of those basis vectors as capturing the essential information needed to preserve the model's behavior on previous tasks,
Okay.
both in terms of its final predictions and those smooth gradients from IGR.
So it's not just projecting weight updates onto a single subspace like GPM does. It's projecting onto two separate subspaces.
One for the layer-wise inputs and another one for their gradients with respect to those input samples. And this double projection is really the key to stabilizing both the performance and the robustness.
So walk us through the DGP algorithm itself. How does it work step by step? Let's say our model is learning a new task. What happens?
So first, the model is trained using IGR to make sure that those gradients stay nice and smooth.
Okay.
But the crucial part here is that during training, the weight updates are projected orthogonally onto those stored basis vectors that were obtained from SVD.
Okay.
And this prevents those updates from drastically changing what the model has already learned.
So it's like the model is walking this tightrope.
Yeah.
It needs to learn these new things, but avoid steps that might make it fall off and forget all those old things.
Yeah, that's a good analogy. Now, after the model's been trained on this new task, DGP performs SVD on both the layer-wise inputs and their gradients with respect to those inputs.
Okay.
This gives us a new set of basis vectors that represent the important directions for this new task.
And those get added to the pool for future tasks.
Exactly. The process just repeats for each new task, building upon the knowledge of the previous tasks, while ensuring that the model doesn't lose its robustness along the way.
Very clever.
Yeah.
But of course, the real test is how well it works in practice.
Okay.
So let's move on to their experimental setup and results.
Yeah, let's dive into that. So to evaluate how well DGP actually works, they tested it on 4 popular benchmarks for continual learning.
Okay.
Permuted MNIST, rotated MNIST, Split-CIFAR100, and Split-miniImageNet.
Yeah, those are pretty standard for continual learning, and they offer a nice range of complexity, too.
Exactly. That way they can get a comprehensive view of how well DGP performs.
And I'm guessing they didn't just use any old attacks to test robustness, right?
Oh, definitely not. They used some pretty strong adversarial attacks.
Okay, like what?
Well, they used FGSM PGD and auto attack.
Oh, wow. Auto attack. That's a tough one.
Yeah, it's considered one of the most powerful attacks out there.
So I guess the big question is, did DGP actually manage to keep that robustness as it learned new tasks?
The results are pretty impressive, actually. DGP consistently beat all the other methods in terms of maintaining robustness,
Really?
especially against those stronger attacks like auto attack.
Interesting. So even when they combined existing defenses with continual learning methods, DGP still came out on top.
Exactly. It seems like having an algorithm specifically designed for continual robustness really makes a difference.
Yeah, that makes sense. It's not just about adding robustness as an afterthought.
Right. It's a fundamental challenge that needs a dedicated solution.
But of course, robustness isn't the only thing that matters. We also care about how well the model performs on the actual tasks.
Of course. We don't want to sacrifice accuracy for robustness.
Right. So how did DGP stack up against other continual learning methods in terms of performance?
Well, it did pretty well. It showed performance comparable to some of the leading methods like GPM and GEM.
Okay, so it wasn't always the absolute best,
Yeah.
but it was up there with the top performers.
Exactly. And remember, it was doing all of this while also maintaining that robustness, which is pretty impressive.
Yeah, that's a tough balancing act, for sure. I remember seeing something in the paper about visualizations, too.
Oh, yeah. They had some really interesting visualizations showing how DGP stabilizes the sample gradients over time.
Could you explain those a bit more?
Sure. So basically, they show that DGP keeps those smooth gradients from IGR pretty much constant as the model learns new tasks.
Okay.
But the other methods, they show much more fluctuation in their gradients over time. And that's probably why they're more vulnerable to those attacks.
I see. So it's like DGP is providing this anchor for the model's understanding of robustness.
Yeah, that's a great way to put it. It stops it from drifting too far off course as it learns new things.
Whereas the other models are more like ships without anchors just getting tossed around by the waves of new information.
Exactly. And that stability in the gradients seems to translate to stability in the predictions, too.
Making it less susceptible to those attacks.
Right. And this really highlights the core challenge of continual, robust learning. Building models that can adapt and evolve without becoming less resilient to those attacks.
It's about making sure that AI systems stay trustworthy even as they become more intelligent.
Exactly. But of course, like any method, DGP has its limitations too.
Okay, let's talk about those. What kind of downsides did they find?
Well, one of the main limitations is this trade-off between stability and plasticity.
Okay, what do you mean by that?
So by making those weight updates really strict to keep things stable, you might end up limiting the model's ability to learn completely new concepts.
Yeah, I see. It's like you don't want to make the model so rigid that it can't adapt to new situations.
Exactly. It's a delicate balancing act.
And are there any other practical limitations?
Well, there's also the computational and memory cost to think about.
Right, of course.
Compared to something like DGP needs more resources because it has to store all those extra basis vectors and do SVD twice after each task.
Yeah, that could be a problem, especially for real-world applications where efficiency is key.
Definitely. But the authors did mention some potential solutions for this.
Oh, like what?
They talked about using rank approximation techniques when that pool of basis vectors gets too big.
So that would help to reduce the memory footprint?
Exactly. You can compress that basis vector matrix without losing too much important information.
So it's like streamlining the model's memory without sacrificing its core understanding of robustness.
Right. And this is a really promising area for future research, especially if we want to use this approach for more complex tasks.
It's fascinating to think about how this research could shape the future of AI.
Definitely.
I mean, the idea of continual robust learning, it has implications for so many different areas.
Absolutely.
Like natural language processing, robotics, reinforcement learning, anywhere that AI systems need to keep learning and adapting.
Exactly. And it's not just about making these systems smarter, it's about making them more trustworthy, too.
Right. So they can operate safely and reliably in the real world, even as they encounter new information and learn new things.
Precisely. Imagine chatbots that are less vulnerable to malicious prompts or robots that can learn new tasks without forgetting their previous training.
It's a future where AI is not just intelligent, but also resilient and dependable.
And adaptable.
Well, I think we've covered a lot of ground today. It's been a really thought-provoking discussion about this exciting area of continual, robust learning.
Absolutely.
And for our listeners, I encourage you to think about that question we raised earlier. Could there be other ways to achieve this continual robustness? Maybe ways that strike a better balance between stability and plasticity. The future of AI really depends on finding those solutions, so keep exploring, keep learning, and keep asking those critical questions.